Okay, good afternoon. So first of all, I would like to thank to Professor Delisola for inviting us to present our work. The title of the presentation is on how to generate non-local constitutive behavior. When we start from lattice models, the approach is such that we can rather easily generate also continuum limits and continuum kernels. The work is a joint work with Bernard Collet. Why does it not change the page here? Maybe F. I think maybe it's not full screen. Maybe it's not full screen too. Is it frozen? No? It works now. Okay, thank you. So now, okay, here's an overview of what we are looking at. First, we look what approaches are there on non-local constitutive models. Then we give some motivation and objectives, and introduce the approach by means of a simple one-dimensional periodic chain, as simple as possible, first of all. And we discuss a simple benchmark example, which we will see. From that we construct non-local Laplacian operators, which are actually the key operators which contain the all constitutive information, and also on the continuum kernels. Then we will discuss how we can, from here we are still in the lattice, in the discrete lattice approach, in the periodic setting, and here we discuss the passage to a continuum model. From this, we will see how from this discrete Laplacian we will obtain continuum limit kernels, which also contain the long wave as eigenvalues, the long wave dispersion relations, and also the elastic kernel is also contained in this Laplacian continuum limit kernels. So afterwards we look at some examples, Gaussian often you probably heard from some non-local models which have a Gaussian type of kernel, which is a very natural choice, which is also can be discussed within this approach. Then you can also do the inverse, solve the inverse problem when you have a continuum limit elastic kernel, for instance a Gaussian kernel. What lattice potential corresponds to this kernel? So we can solve the inverse problem from the kernel to the elastic lattice potential. Then we discuss some conclusions, outlook, and we have, as we have heard today, we have some new common lines with the work of your Francesco. Then we have this is by means of a one-dimensional chain with where each lattice point is one atom. We have also generalized it when we have a polyatomic chain. So we have unit cells with n the number of n atoms or n degrees of freedom per lattice per unit cell. So I will only very short discuss this. So we have previous works. We have all this machinery of lattice dynamics, and non-locality was mostly discussed with some spring model with some next a few neighboring springs. These are the common quite a lot of models which exist. And on the other hand, we have continuum theories, non-local continuum theories, which were introduced in classical seminal papers by Ehringen, Kröner, and others. And what is fairly rare is a connection how the continuum non-local models are linked to a lattice non-local model. So there are very few works which tackle this problem, and this is a bit the motivation of the approach to have a systematic procedure which links both continuum models and lattice models. So the advantage of the approach we are going to see is we have a very simple formulation of elastic energy. We are only in the harmonic approximation. Then we have any harmonic potential can be expressed in this approach, as we will see. And we have, without further calculation, directly can get out the vibrational dispersion relation and dynamic characteristics of this system. And because we can apply to any constitutive behavior, it gives really a method which easily allows to access important dynamical information of the system, and it allows straightforwardly calculate continuum limit kernels with the procedure we will see. So the complete constitutive, so we start now by claiming that the complete constitutive information for the one-dimensional chain can be condensed in a single scalar function which we call characteristic function. So it contains all. So let's first of all consider what kind of system we look at. So we have a periodic, a cyclically closed chain, which you can imagine a ring chain, where the nth particle is the first particle. So we have n degrees of freedom. P are the lattice points, and when we go to jump to n neighbors further, we make just one round in the ring, and we are in the same particle. So now convenient will be when we have a lattice sum over all atoms of the chain. We can we introduce a density such that it can be written as an integral, and the density can be represented as a sum of delta functions. It's normalized that integral of the density is the So yeah, we have been here we have cyclic. What is this? We have cyclic boundary conditions, as we said. So P is to be understood as a cyclic index. So in the, when we write the total energy with this density, can be easily written with this. It's actually a sum over all lattice points, and H is the Hamiltonian density, which has here a dimension of energy, because rho has a 1 over length dimension. So now let's consider a lattice potential. So I have to define, maybe, did I define it before? Or? No, not yet. So yeah, here it's very useful to define the shift operator. So dH is the operator which shifts the displacement field by the argument of the displacement field of amount h. So if h is a lattice distance, it shifts the particle from point xp, from lattice point xp to the neighbor. So if you can generate differences of next neighbors, you can write it shift operator minus unit operator applied on x at x equal xp. So why we do this? Because it allows us to generate higher order differences in a very what is here is in a very compact manner. So we can write second differences as just a quadratic function of the shift operator, and so we now generate a non-local harmonic potential such that it is a quadratic form of mth order differences, symmetrical to the left and to the right when x is a lattice point. It involves m next neighbors to the left and to the right. So why we do this will turn out a bit later. We can generate arbitrarily high orders m of orders m potentials, even in a chain with finite particle numbers m, because of the cyclic condition. So if m exceeds n, it doesn't matter. So it is still on the chain, is defined. So the mth order operator is here defined as a in the usual way of binomial decomposition. So further we can generate more. So this is on the lattice. So we can generate now, consider now, linear combinations of different orders m. In general, just a series of all orders m with these harmonic potentials which we introduced just right now. Omega m square are characteristic frequency, so mu is the mass of the atom. So these are actually characteristic stiffness constants which characterize the interaction of order m. Note that here this operator applied on ux, this is a linear function in the displacement field, so this is a quadratic form in the displacement u. So it's a harmonic interaction, and we define now we allow only a combination that it should be converging and positive. So that means all am can be, we introduce here a coefficient am which can take either vanish or change the sign of the order, and but the whole series should be positive. So we can formalize this again a bit more. First of all, we introduce a characteristic function f of lambda such that it is converging and that it is positive in this interval. We will see in a minute why it should be in the interval between 0 and 4. Further, it requires that the coefficient with m equal to 0, translational invariance, should not change the lattice energy. So the lowest order should be absent in this series. So we will see that we can any harmonic potential write in such a series for any harmonic interaction on the 1D monoatomic chain. So here a very useful observation. This is more technical because we have a periodic chain. We can change indices, so we can write this here as a displacement operator D, as we introduced it here, and we can here deduce some matrix relation. D plus is the adjoint shift operator, which is, and because we have periodicity, it is D minus H, so it shifts to the other direction. So in general, it's actually nothing but an expression of the general relation. When we have a scalar product here with operator A, we can transport the operator to the other side by adjoining it. In this way, we can now more compactly write the lattice potential we have here introduced as a series. We can more compact write it in a form. So we can now, these quadratic terms, we can write them in such a form that here is a symmetric function in the displacement operator here, which is totally commutative. They commute, so you have here a discrete Laplacian. So this is the operator of a second order difference with the next neighbor. When you have only next neighbor springs, you have only this guy here in the Born von Karman chain. But we have here any orders of m, and so you can now sum up and use the definition of the characteristic function. Then you see the harmonic potential before can be written as in terms of the characteristic function, where the argument lambda is now replaced by the second order difference. So any elastic energy on the chain, you can write it in this way with a simple, here this characteristic function which contains all information which we will see in a minute, and it makes very easy any calculation, because so this is the Born von Karman. If you have a monoatomic chain with only next neighbor interaction, then your f is here just to the argument itself. Then it's a very trivial case. You have the Born von Karman chain. This can be then written in sum of. In that case, you have here only orders, first order, so it's the normal next neighbor chain as we know it. So it's included as a special case. So why is it very convenient? So you can now define this as a Laplacian in the equation of motion. This guy here, it's already, I switched too quickly. You see the negative characteristic function multiplied by the mass is nothing as the Laplacian matrix, which appears in your equation of motion of the chain. So you can here easily determine the dispersion relation. So let's, for instance, have a quick example. If you have a spring model of n's with springs to the nth neighbor, then you have terms in this form. Then you can write the characteristic function. You have a Laplacian here in this form, which is a second order difference between n's neighbors, and now you want to express this in first neighbor Laplacian, and you can, by a very short calculation, you find it in the form of such polynomials. Here's a double misprint, by the way. Here this should be a plus, and here this should be complex conjugate. So the whole thing is real. So our equation of the Hamilton variation principle very easily gives you your equation of your Laplacian operator, where the following properties are very important, because we define the characteristic function as we did. It has all good properties of a Laplacian. It's self-adjoint. It means it is a symmetric function in the displacement operators here. It is negative semi-definite, which means elastic stability, which was guaranteed by the positiveness of the characteristic function, and translational invariant because it starts with order 1, so parallel displacement does not contribute to the elastic energy. So now dispersion relation, we all know in the dispersion relation of the Born-von next neighbor thing, we can directly see that it's here a 4 sine square, very well known relationship. And so we can, in our general non-local case, it has is just directly the characteristic function by putting the argument to the eigenvalue of this guy here, gives you directly the dispersion relation of your non-local chain in this form without further calculation, because it's an operator matrix function of this fairly local Born-von operator. So now, why is it practical? Because we see not only that we can directly get all dispersion relation information, we can also get continuum limits of interest. For instance, when we have a periodic string, we can we let the length of the chain we keep it finite, but the lattice spacing tends to 0. So we have we get more and more particles as a dense chain limit actually. And we can later let L to infinity, then we have an infinite medium limit. So now to make this approach useful, we have the following, have to do some hypothesis. Namely, the hypothesis we do that all extensive physical quantities, such as the elastic energy, are all quantities which scale with the size of the system. They should remain finite in the continuum limit. So especially the elastic energy should remain finite, and the entire mass of the string should remain finite. It does make sense when the string becomes infinitely heavy or infinitely light. Also, if the elastic energy would tend to 0 or to diverge, it would not be would not make any sense. So it should be all these quantities should remain finite. When we do this very simple hypothesis in the beginning, then we find scaling. We have the following scaling behavior, necessary scaling behavior of the mass of the particle. Namely, it must scale as the lattice spring. So it must be a constant density multiplied h must be the mass of the particle. So the particle must become lighter and lighter, that the mass stays constant. This is rather trivial for the mass, but more interestingly for the elastic potential. If we now look on the nth order of this series in the characteristic function, in the potential, we have the requirement that the nth order must stay finite when h tends to 0. That here, because here we have the mass, scaling of the mass, we know it already, and we now the only condition which we can impose is here that this characteristic coefficient of frequency must have a certain scaling behavior to keep it finite. So here, the second difference of order m, when we consider it as an operator function, so d we can actually, this is maybe, should have said it, d could be can be as an exponential of the gradient, so to say, of the derivative. And if we write it in this form, we have here this operator form of this representation. And of course, this second difference, it tends to h square second differences. So you get in the Born-von chain with only one next neighbor, you get a second gradients in the Laplacian. Here, this is the Laplacian. And the scaling with h square. in the order of m. This is nothing but the definition of an m's order, even order, 2m's order derivation, with here with a very important multiplier which occurs because the whole thing is positive. So this leads to the requirement that when this is remaining constant, this must be inverse scaling as the operator, leading to the requirement that your characteristics, frequencies, need to scale like inverse powers of h. So if you then utilize the, here you have still a lattice sum, but here you have this scaling of the mass, which gives you the dx, so to say, in the continuum limit. Then you have this is transferred to an integral, which here gets our density of the m's order, just a quadratic form of displacement field, and second order even orders of derivatives. By partial integrations, by the way, you can transfer this in quadrats of m's order. This is, you can also do the continuum limit. When the continuum limit is made, here started with a moment. Where's it? When you do the continuum limit starting with the where is it? Yeah. When you do it here with the quadratic forms of m's order, you get quadrats of m's derivatives. So you can also directly, so you get gradients of any orders, a series of gradients of any order. So, moment, sorry, I went to the wrong direction. Yeah. So, yeah, you can now you can introduce a function, a continuum long wave or continuum limit characteristic function, which has here this rescaled or renormalized coefficients. Remember the lattice characteristic function? No, I went to the wrong. This is here the rescaled the rescaled long wave coefficient, and it's enough when this for an order which is not vanishing, when this is asymptotically for h to 0 fulfilled. It is enough, and it can also be certainly it's allowed that there are certain orders do not fulfill this scaling, can tend to 0. Then you can have here vanishing order, so Bm takes account to this fact that you can have a truncation of constitutive information of the lattice. So you can, if you have this scaling, then you have the Bm is 1. If you have a weaker scaling, then it can vanish, and the new continuum limit characteristic function must be such that it's again elastic stability is maintained. So this gives you also imposes you a condition of not all Bm can be 0 simultaneously. If all Bm equal to 1, that means all orders M have this scaling behavior. Then the whole constitutive information of the lattice is maintained in the continuum limit kernel. This is if we make this assumption, then we can later reconstruct the lattice characteristic function from the continuum characteristic function, which allows later, we will see, from the continuum kernel to reconstruct lattice potentials. We will see this a bit later on some examples. So how this, here again, the continuum limit elastic potential with here this new function, which is a series generated by this rescaled coefficient. And it's very important, this operator is positive definite. The eigenvalue is k square, and the function is positive, so it's a positive. This is a positive operator, and this the Laplacian continuum Laplacian is negative definite, as it must be for a Laplacian. When we write this as a sum, here's the periodic delta function, so representation of this in a distributional representation. If we write it in here, then we have see what kind of gradients are intervening here. It's important that it starts with m equal to 1, so the b0 must be b1 must be 1. So the first coefficient is actually the usual Laplacian, as we from the if we have a Born von Karman chain, we have only this term, then we have only the second derivative. But here we have all in general all orders. And interesting thing is when we have here, we can also get out the elastic moduli kernel. It can be seen that this is connected just by a second derivative of with the elastic kernel. I think here's a minus missing, but okay. So the distribution of the elastic this is correct here. It's positive definite. Elastic kernel must be positive definite. So we have here a series representation in distributional sense of the elastic kernel, which correspond to the previous lattice potential which we introduced. Because it works for any lattice potential, in principle we can determine any kernel. So let's and the same also with a dispersion relation. By doing the we know the dispersion relation has this simple form in the lattice setting. In the first Brillouin zone, we can now make the continuum limit, and it occurs here the characteristic continuum function which we have defined just right now, and we get here the continuum dispersion relation in this form, certainly positive, because we have here the restriction, made the restriction f tilde is positive. So in the non-truncated case, when all Bm are equal to 1, then the long wave dispersion relation contains the entire constitutive information of the lattice chain and allows to reconstruct lattice potentials. So we will, because it looks maybe a bit dry or abstract, so we will now demonstrate in a let's now consider an example. Assume you have a Gaussian, a one-dimensional, infinitely long chain with a Gaussian elastic modulus. So we want to know now what kind of lattice potential corresponds to an elastic Gaussian modulus when we assume no truncation, when we assume all the Bm are equal to 1. So if we assume all the no constitutive information has gone lost in the continuum limit. So first, the first step, construct the continuum limit characteristic function, which is because of the relation minus, because of this relation here. Where is it? Here? No, I went to the wrong direction maybe. I went other way. No, it's the other direction. Because of this, we have an easy relation between Fourier transform of elastic modulus and continuum limit characteristic function. And here, which allows us here, because of the Gaussian, the Fourier transform is here straightforward. So this allows here directly come to the continuum limit characteristic function, and by taking into account the scaling relation between these coefficients, when this is true for all coefficients, we can reconstruct the lattice characteristic function by replacing the argument here wave number by this guy here. And this expressed as a function of lambda is the lattice characteristic function, replacing lambda by the second order Born von Karman Laplacian by regarding it as a matrix function is the Laplacian operator of the discrete system which corresponds here. If we have this, we have also the potential, which then simply is here this quadratic form of this lattice Laplacian with this. Because we have this in closed form for the Gaussian, this is kind of a Gaussian exponential dependence where this k square here appears here as in operator form. So this is a lattice potential which exists on the periodic chain, which is on the periodic finite chain, which corresponds to this Gaussian kernel, by the assumption of non-truncation of constitutive information. Some more details, you can find it here in the article, which I have with me, so I can pass it to you. So for some technical details there, and yeah, so only to have something a bit not too Bourbaki, it must rather Bourbaki maybe. So we have also made some pictures. So if you have now introduced a very important thing here, I forgot to say, sorry. The first order always of this dispersion relation, it corresponds to the next neighbor, Born von Karman, and the rest is something which makes the non-locality. So here we can introduce the higher with the higher orders, which are summing up. So the first order m equal to 1 is here, and the higher orders give rise to this factor, where we can characterize this here as a non-locality parameter. When the non-locality parameter is equal to 0, but then we have local Born von Karman behavior, next neighbor chain, and if we switch on the non-locality, we have here this modified dispersion relation, which we now can have a look here. So gamma equal to 0 or almost 0 is Born von Karman, sine square here in the first prior zone, but we can, by switching on, we can here generate rather unusual behavior. For instance, we can create a new maximum here within the prior zone. Here outside it's always 0, but from symmetry reasons. It's also clear because the characteristic function is a function of sine square, and it can be shown that the derivative always by the chain rule, you see derivatives on the borders of is always 0. So you have all these necessary conditions of a lattice model you have automatically included, and including you have always elastic stability of your lattice model as well as of your continuum model. So that's what we talk. Okay, here you can also plot the group velocity and this unusual behavior with a new maximum is here by 0 in the group velocity. So this is kind of a behavior which you cannot find in classical crystals with only next neighbor interactions. So you can generate new dynamic effects by this non-local models. So now we can further this. So far we looked up to here to a chain. This has only an arrangement of 1 atoms, but when we have now a unit cell with n atoms, we can elaborate the approach as well. In this case, the characteristic function becomes an n times n matrix in the number of atoms per unit cells. These coefficients am, which were before scalar coefficient with the scaling behavior, become now matrices, and the scaling behavior is mapped on the eigenvalue of the matrices. This n times n matrix determines then the eigenvalues of this n times n matrix, determines then the dispersion relation. And all this postulate what we said about the characteristic function is now true for the matrix. So positive definiteness and so on must be now true for this n times n function. The n eigenvalues of this function give the n branches of the dispersion relation. We have here the admissible characteristic matrix here must be chosen such that you have n eigenvalues, n minus 1 eigenvalues always positive. This allows you a 0 order here, and 1 order where the 0 order is vanishing, which defines your acoustic branch. And the eigenvalues of this, when you replace your lambda again by the eigenvalues of Born-von Karman lattice, these eigenvalues define your dispersion, your branches of dispersion relation. So in this way you can easily generalize this to crystal, to also 3D crystals and to higher dimensions, not only to 1, but we elaborated here first for the sake of simplicity to 1 dimension. So here, here an example for a diatomic chain. So per unit cell 2 atoms. We have 2 branches. One is the acoustic branch here, and the other in 1 optical branch. And here for different, here for a mass ratio, which I think from an atom, from a realistic system, right, is chosen a kind of which appears in a certain material system. I forgot it, which one. And for different degree of non-locality, alpha equal to 0 reproduces here the classical results known from crystal physics. You can see it in find it in the book of Ashkar. I think this kind of 0 order classical dispersion but in any book of crystal physics, voila. And here you can find this model in a recent, in this reference you know well in the meantime. So this maybe it's all what I wanted to say, almost. So when maybe to summarize,
Applied mechanics.
Did I? Oh, sorry, yeah.
Archives of mechanics.
Sorry, This is true, I will correct it. So, just to conclude, we can, for the 1D monoatomic periodic chain, it can be shown that we can write any harmonic potential in this kind of framework by utilizing characteristic functions. And we have a direct, it gives a direct interlink between lattice and continuum model in both directions. Either when we have a continuum model, we can reconstruct lattice model and vice versa. And we have the characteristic function contains the entire constitutive information in very compact form, and by only assuming finiteness of elastic energy we get scaling relations of the coefficients which allow this, and we can also generalize this approach. We have worked it out for 1D periodic conditions, but as soon you know the function space of your displacement, you can generate also in other frameworks this formalism, especially for periodic 2D, 3D. It's rather, you can generalize it. However, here there's an additional problem of anisotropy coming into play, which is absent in the 1D case. We only have to deal with symmetric operators. So the symmetry self-adjointness gives us already the symmetry, but we have here additional crystal in the higher dimensions. We have to have crystal symmetries which would have to take into account in the difference operators, different directions. So there's a complication in there. Okay, here again the references. Here's okay, right? Okay, so thanks. I think this is all. We can discuss this now further. And
Thanks.
yeah, when you have some questions,
we explored the chapter along here. We have another talk.
okay. Yeah.